that aims at telling you a little bit about the Liquid tools and how we use them for resource-based node-level analytic modeling and making sense of the performance of codes. My name is Georg Hager. I'm here with my colleagues, Christie Alappat, Thomas Gruber, and Jan Laukemann, who did all the heavy lifting. So I'm just doing the introduction into resource-based node-level analytic modeling. Here's the agenda, very rough agenda for today. So I'll spend like 15 minutes with this introduction. Then Thomas Gruber will give an introduction to 3 of the Liquid tools: Liquid topology, PIN, and perf counter. Perf counter is, as you might have guessed, instrumental for all this performance engineering efforts. And then finally, Christie and Jan will give a live demo using a code that we usually use for our node-level performance engineering courses, a matrix-free conjugate gradient solver. And we recently got it to run on A64FX, and we'll show you some interesting results when approaching a code that you don't know by heart from the beginning. So how to find out what's going on in such a code. And then we can have a freestyle Q&A at the end. Okay, so the main question we ask ourselves when we approach performance problems is, how much of some resource, and this is usually time, sometimes energy, does some stuff that we want to run take on some hardware, and why? And the why is very important. If you leave out the question why, then you can do all sorts of blind, like black box modeling with curve fitting and machine learning. You get wonderful models and predictive models, which are useful in some contexts, but you don't get much insight about what's going on. And this is why we stress this why so much, and why we try to set up analytic, resource-based first principle models that give us a clear indication what the bottleneck is and how we can probably fix it. There's a very important distinction between 2 like schools of modeling, and I call them mechanistic and resource-based. In mechanistic modeling, we look at the hardware and the software on a cycle-by-cycle basis. It's like a huge collection of cogwheels or little clocks that keep ticking and that do things independent of each other. Latency is the major metric here in this point of view. If you want to do it right, you quickly end up with setting up a simulator-like software that somehow tries to simulate the hardware as closely as possible. And mostly the conclusion will be it's very complicated and it's really hard to find out what the actual bottleneck is. Resource-based modeling is a little different. It doesn't think about clocks ticking. It thinks about stuff flowing. So how much is a resource utilized? What percentage of the resource is utilized? How does data flow through the system? Which of the components that make up the system can work at the same time and which cannot? And for resource-based models, the nice thing is you can simplify them to a point where it's almost unrecognizable as a model for the actual hardware, but still they can still be useful, even if they're very, very simple, like the naive roofline model I've shown here. Okay, so this is the way of thinking resource-based modeling. Now, of course, we cannot model everything with that. The typical point of view we take towards running code is we have alternating compute-communicate cycles. If we're on a single node, communication usually boils down to something like synchronization, like barriers or other synchronization constructs. And usually we also assume that these compute times, they comprise parallel loops of some sort, and those parallel loops are long, so that startup overheads, wind up overheads, and so such things are negligible. So we assume some kind of steady state. Okay, and then we try to set up a runtime model that is some kind of function of the stuff we want to run, so the application and the hardware. So we distinguish between a machine model and an application model, and try to find out in which way they interact. Okay, so in order to make this a little bit more mathematical, just slightly, a general view on used resource bottlenecks. What is the maximum performance when limited by a bottleneck? That's our main question. So we think about bottlenecks, and each of those bottlenecks can deliver a resource at some maximum rate. So bottleneck number I can deliver a resource at a maximum rate, Ri max. Now, if I want to utilize this bottleneck, I want something from it. I want a certain amount of resources, which I call Wi. And then I know the amount of resources, I know the rate at which they can be delivered. So these resources have to go through this bottleneck, and of course it's very easy to find out then what's the minimum runtime when I'm only limited by that particular bottleneck. It's just the amount of resources divided by the maximum rate, and there might be an additional latency term, but often we can neglect that. Okay, so this is like the minimum runtime when I'm limited by a single bottleneck I. And of course, there are multiple bottlenecks on our computer system. So I have multiple minimum runtimes. And in some way, I have to find a way to plug them together in a function to get some expected runtime. And this is the whole secret. What's this F function? What's the function of all these minimum runtimes? How do I have to put them together to get an expected runtime? That would be my performance model. It's actually a runtime model. We like to think in terms of runtimes instead of performance because it's much more flexible. It allows you to incorporate many more effects than just thinking about two bottlenecks that give you one performance number like the roofline model. And then, of course, the overall performance is the overall work, whatever that is, iterations, flops, mask operations, whatever, divided by the expected runtime. Okay, that's then the final step, converting from runtime to performance. Okay, very simple example, and sort of like to make a bridge to the well-known roofline model. Let's say we have the simple loop, DAXP like A of I equals A of I plus S times C of I. This loop has a length of 10 to the 7. We're dealing with double precision variables here. It's long enough so that any startup and wind down effects are unimportant. And we want to run this loop on this N-core CPU. Let's say this is one CMG, one core memory group of an A64FX at 2 gigahertz. And then I can do the math and see what are the two main bottlenecks in this core memory group. Of course, it's the maximum flop rate, that's 768 gigaflops per second, and the maximum memory bandwidth is one CMG, 1/4 of an A64FX, that has a bandwidth of roughly 210 gigabytes per second. Okay, these are my bottlenecks. And then I can calculate how much time it takes to execute the flops and how much time it takes to transfer the data. The flops is 2 times 10 to the 7. The data transfer volume is 3 times 8 bytes times 10 to the 7 bytes, obviously. And then these are my two predictions for the 2 times. The flop time is 26 microseconds. The data transfer time is 1.14 milliseconds. So these 2 times are my 2 component runtimes. Now the big question is, how do I plug them together to get a prediction? Of course, there are 2 like extreme cases. I could take the view of a very pessimistic model, so no overlapping of these times at all, which means I would have to add them up, okay, at these runtimes. In terms of our simple 2 bottleneck model, that would mean whenever the CPU calculates something, it cannot transfer data and vice versa. Or the most optimistic model would be a full overlap model where any kind of computation can fully overlap with any kind of data transfer. And then, of course, the function is a maximum function. And this should be familiar because this is the roofline model. Okay, it doesn't look like it in this form because it's a time-based formulation. And you see the power of this time-based formalism because we can, at any time, we can add more times here, and it's still a valid model. In the roofline model, you're having a hard time incorporating more bottlenecks. You have to introduce multiple roofs, and it's not really clear what the x-axis means, and it's just more powerful if you have multiple bottlenecks to think in terms of times. But this is a roofline-like thinking. This is already very old. So 1989 is the oldest paper you can find where this kind of thinking was published. Okay, so for our example, of course, the 1.14 milliseconds for transferring the data is the largest of those 2. So the minimum runtime for the whole program is 1.14 milliseconds, and this amounts to 17.5 gigaflops per second. Okay, this is what the roofline model gives you in this simple scenario. Of course, roofline only considers 2 bottlenecks, and we know that hardware is much more complicated, especially if you look at single core. And you will see later that single core execution is decisive. It determines, for example, whether or not you're going to be able to saturate the memory bandwidth. So a refinement of the roofline model is the ECM, or execution cache memory model. It considers all the time components it takes to, for example, transfer the data from memory to the cache hierarchy, within the cache hierarchy, and also the time it takes to crunch the data once it has arrived at L1, so that all the data comes from L1. Then I can do my stuff, my work in the registers, and this also takes time. And of course, then the number of time components can become quite large, 3, 4, 5, 6, 7, depending on what I'm looking at. And the overlap function, or this function f that determines how they're plugged together, could be quite complicated. And of course, in order to find out how much time each of these things take, I also need to look at the code, because in order to know how much time it takes to get the data from L2 to L1, I need to know how much data is there to be transferred. So that's something that comes from code analysis. I have to know that. For a simple streaming code like the DAXP, I know that it's 24 bytes per iteration. For a more complicated code, it may be more complex. Okay, so you might wonder, and this question always comes up, can we automate this stuff? Some of it we can. I won't explain this figure. It's a part of our recent paper that we published, where the whole ECM modeling workflow is like shown in an abstract and well-defined way. And some of these components can actually be automated. OSACA is the open source architecture code analyzer tool, which is constructed along the lines of IACA from Intel, which doesn't exist anymore. We will have to say something about that later. And Contraft builds on OSACA and tries to automate the complete modeling workflow for some kinds of loops, not all of them, but some restricted loop structures. So if you're interested, you can look at these papers. Okay, so a couple of overlap assumptions just to get you started on this. So what could happen on actual hardware? If you look at Intel Haswell, and we look at all the data transfers to the cache hierarchy and what's going on the core, then this is the overlap structure on Intel Haswell. Whatever happens in the cache hierarchy and the memory hierarchy does not overlap at all. So all these time components add up, okay? Everything that happens in the core, so all arithmetic and also the stores, that overlaps with this data delay column. This is how Intel processors work, and this is how they still work till this day, at least until Cascade Lake. AMD Zen 1, Naples, works a little differently. Here, the L2 cache is overlapping, and it's much more overlapping than it looks here. So this is one of the reasons why the single core memory bandwidth on AMD processors, on current AMD processors, is much higher than on Intel processors. They have a much more overlapping cache hierarchy, and this has improved again with Zen 2. Zen 2 has an almost completely overlapping cache hierarchy, and there's almost no serialization in the memory hierarchy. Skylake is again completely serializing. Since we have a victim L3 cache, there's even more penalties. So that's why over a time span of 10 years, we haven't seen a significant improvement in single core bandwidth on Intel processors. And the reason is this serializing cache hierarchy. For A64FX, it is more complicated, and you can look it up in the paper. We have a partially overlapping L1 and a fully overlapping L2. This is for the FX1000, where we can use large pages. For an FX700, it's a little bit different. And if you want, we can discuss this later. All right, so just to get you started. Now, what do we do if we can't set up a model right away? We cannot analyze the code or don't know enough to analyze the code. We can measure stuff, and we can do that with liquid perf counter, for example. So things we look at, and this will be also the topic of later talks. I can look at IPC, number of instructions executed, memory bandwidth versus saturated memory bandwidth, how much of bandwidth is utilized, how many floating point instructions are executed versus all instructions. If I have a floating point code, but only 2% of the instructions are floating point, then obviously something is wrong. Floating point arithmetic versus loads and stores, also quite interesting. How many loads and stores are there? Could indicate, for example, spilling. SIMD width of instructions, if that's available as a metric. It's not always available. Cache line transfers versus instructions, so how many loads and stores and cache line transfers are there, and is this reasonable? And in addition, we can look at some other observables, like scaling behavior. Does the code scale across a NUMA domain or does it not? Okay. How does it behave with respect to problem size and other parameters? And finally, from these, we formulate some hypotheses about what's going on, and then we test these hypotheses, again, with new measurements. So here's a table of example scenarios. That's just a very quick overview of some things that could happen and some things that we're also going to visit later in the code analysis. So for example, I could observe a good scaling of performance across the cores of a NUMA domain. Okay, the hypothesis I have about this is the code is not data hungry. It's not data hungry enough to hit the bandwidth bottleneck. All codes need data, but this code just doesn't need enough data to hit the bandwidth bottleneck. Now, what could I do now? I could find out stuff with LIKWID. So for example, is the code just a high intensity code? Does it do a lot of work? Or maybe it's plagued by pipeline stalls. It's waiting all the time for stuff to happen, and the pipelines are stalled, so that's why the code is not data hungry. Maybe it's executing lots of instructions because it's so convoluted and abstracted that the compiler couldn't produce efficient code. Or maybe there's a lot of in-cache traffic, a lot of traffic that goes on in the cache hierarchy, and then just a little traffic hits the memory because there's so much traffic taking so much time within the cache hierarchy. All possible scenarios, all of those can be explored with LIKWID. Another scenario, I could measure the memory bandwidth, and it's at the limit. Okay, that also means usually that the performance versus number of cores saturates, and the hypothesis, of course, is the code is memory bound. So what could I do? Of course, the only thing I could do is to make it faster, try to reduce the memory traffic. For example, using more compact data representations, like in sparse matrix computations, reduce the amount of data you need for the index, for example. That's a typical straightforward optimization. Or just do less work. Of course, that's very algorithm specific. Or I could employ some ingenious blocking algorithm that just makes better use of the data loaded from memory. Another scenario, the memory bandwidth is not at the limit, so I'm far away from the memory bandwidth limit, but the code is also not scalable. So the limit cannot be the memory bandwidth, so it's not bandwidth bound. Typical hypothesis would be load imbalance. It could also be synchronization overhead. Okay, stuff that's not like not doing anything for solving the problem. I could explore that with LIKWID. I could use it to measure the actual workload across cores to see if there's really a bandwidth, if there's really a load imbalance. And I could measure the instruction count versus number of cores. When the overall instructions versus number of cores goes up, this means there are more instructions executed as I execute on more cores, and this indicates usually some kind of synchronization overhead problem. And then finally, my code could probably not scale across NUMA domains. It could be well understood on a NUMA domain, maybe memory bound, but then across NUMA domains, it doesn't scale. Of course, the hypothesis would be there's no proper parallel data placement in the NUMA domains, no first touch, for example. And I also could explore this with LIKWID. I could measure the memory bandwidth balance across domains, so measure it in every domain and see whether it's balanced. And if it's not, well, that indicates some NUMA problem. Also, on some architectures, it is possible to measure the cross-NUMA traffic, the data traffic between the NUMA domains, so that I can immediately measure how much data goes around between the NUMA domains. Okay, and this list can be extended, but these are just a couple of scenarios. Okay, that finishes my part. And I'm handing over, sorry, any questions? I know this was very quick, but it was supposed to be. All right, then I think it's Thomas' turn. Yeah, Thomas' turn.
So here, let's go on with the first part of the LIKWID introduction. So my name is Thomas Gruber. I'm the main developer of LIKWID. So if you have any questions, I probably can answer them. As Georg has introduced, I want to talk about LIKWID topology and LIKWID pin. So that's the first part. And then we go over to a second presentation with the perf counterpart. So let's see. Yes. So there are many tools out there for node level performance engineering, maybe not directly used for that or meant for that, but they can exploit for that. So to get some node information, most people look at proc CPU info to get some basic view. Also other tools like NumaCTL and HWlog, with all of these output modules provide valuable insight. On the LIKWID part, we have LIKWID topology and to some extent LIKWID power meter, that gives you information about the node, how are the threads distributed in the sockets, in the NUMA domains, and so on. I will show you an example in a few slides. Then very important to get a good performance and to probably place data, you can control the affinity of our application threads, so OpenMP and also MPI processes to run only on specific cores. So we reduce the amount of available CPUs for them. There are also a lot of mechanisms to do that. OpenMP and MPI have their own commonly vendor-specific implementation to do that. With HWLock, you can do it. NumaCTL provides some functionality. And from the Liquid tool suite, we have LIKWID Pin. Then there are runtime profilers, not commonly known like gprof and perf, but also more sophisticated tools like HPC Toolkit. Performance analysis is a huge field. There are graphical-based analyzers like Intel VTune and HPC Toolkit, but also like tools that can be integrated into applications like PAPI. And also from the Liquid tool suite, we provide the Liquid Perf Counter tool, which I will introduce later. Most commonly known is also Perf, so the Linux own performance analysis tool. The last section is micro benchmarking. There we have stream benchmark, which is used by everybody to measure the memory bandwidth. In Liquid, we have Liquid Bench, which is a more like low-level approach to these to kernels like memory copy and stream and so on, but also LM Bench, UArch Bench, and so on. So Liquid, it's an abbreviation. It's the abbreviation for like I knew what I'm doing. We provide some videos at the YouTube channel. You see the link below. The slides are available to you in a Dropbox folder. Georg has posted the link in the chat. It's an open source tool collection and library developed at RSZE since 2009, and everything is provided at the GitHub repository. So check it out. There's also a huge wiki. I'm trying to document everything that is featured. So let's go to the first tool. As an introduction, it's mainly focused on command line tools. We don't have graphical front ends, or there is a little one, but that's not really the main focus. It's easy to install, so normally this make install scheme. It works with standard Linux kernel interfaces, so no need to patch the kernel or anything. All functionality is provided with standard Linux kernels. It's simple and clear to use. We try to focus something like on this Unix philosophy with small tools that do one job well. So we don't have these huge feature set in a single tool, but more focused tool usage. It supports most of the x86 CPUs. So most is like, I try to add all, but sometimes I'm missing like some laptop chips and so on. But since version 5, we also support ARM7 and ARM8 chips, also Power 8, Power 9, and some support for NVIDIA GPUs. We're currently extending that to AMD GPUs and Intel GPUs. Here are also again a short list of the tools. So topology, pin, perf counter is what I introduce now. MPI run is the tool focused for MPI plus X applications, so to measure and pin applications on multiple nodes. and the LIKWID bench micro benchmarking tool. So how to look at a node? So how does a node look like? Where are the compute resources, and so on? Is easily viewable with LIKWID topology. We have a video introducing it. I'm directly stepping in and showing you the command line output of an A64FX node. So that's the Okami cluster. There you see at first some basic information here on top. The A64FX has no specific name, so this field is empty, but the type is there. So everybody, if you send somebody some output, he knows directly on which architecture it is. Then we have the hardware thread topology, how many sockets, how many cores, is there some SMT active? So on A64FX, there's nothing like SMT, so only one thread per core. Then we have a list of all the hardware threads. So I shortened it a little bit. So we have all the cores with the thread IDs, core IDs. Die is a pretty recent addition to that list. The socket and whether it is available for you to use. So if you're on a cluster, you normally in a job, it might be that you are restricted to use only a few cores. And if you do a LIKWID topology, it shows you with the star marked which cores are available for you. Then we have some socket list, which shows you which core is on which socket again. And then we have the output for the cache topology. On the A64FX, we have two cache levels. So here the two separated sections. The size of the level 1 cache is 64 kilobytes, and it's a private cache. So each core has a own 64 kilobyte chunk. The level 2 cache is shared by all cores in a CMG. So by 12 cores, and it's 8 megabyte in size. So it's easy to look at the output of so the assembly, how it is assembled in the machine. At the last section, we have the NUMA topology, which shows like all 4 NUMA domains, which cores are in a NUMA domain, the size and the distances. So how far it is virtually to communicate between these NUMA domains. The output is quite similar to the NUMA CTL output. We can make use of this architecture to pin our thread and processes with LIKWID pin. We have also provided a video at our YouTube channel with some introduction. So why do we need pinning? So if we don't pin, there's basically anarchy on the node. Each thread is scheduled on a physical core. The operating system is deciding to move them around. And that's what we see here in this picture. So that's a basic stream. Try it from the stream benchmark without pinning. And we see that with increasing core numbers, the error bars get larger. So we have huge variation in performance. If we start pinning, so that's the picture here on the right. We see that there is almost no fluctuation anymore, and we have this saturation curve here in the first part, and then we have the funny linear scaling, which I will try to explain on the next slides. So there are several reasons to care about affinity control. So it eliminates the performance variation, as we see here in these two pictures. It makes use of architectural features. So like if we have polluted our cache with data and then we move the thread away, we have to reload the data into the new private cache. So if we want to make use of the cache, we have to ensure that the application thread is not moved away. And it also avoids resource contention. So if we have like the memory bandwidth is commonly a limited resource, and if we schedule too many threads on a single memory domain, it might be we have resource contention. So if we use more of the domains, we can avoid that. So there's something in the chat. Okay, nothing for me. So here's a short explanation why we have this scaling behavior. If we fill our threads in a compact way, so we start with a single core and we add the cores up until we reach the numbers of cores per socket, and then we start adding single cores of a different domain to that. We have this picture. If we use scatter pinning or spread pinning, so we fill both sockets at the same time with two threads. In that case, we have a completely different scaling behavior. And the reason for that is that by the implicit barrier at the end of OpenMP parallel or parallel sections or the do loops, we have an implicit barrier. So if we look at how the work is distributed on the socket 0, all the threads are fully occupied with work, so take the full time. But on the second socket, the memory bandwidth is not fully used. So each of the threads can get more of the available memory bandwidth, and the remaining part is spent in waiting. So we wait at the barrier, and this is exactly what we see here. So these threads have more are these threads which have waiting time in the end. So here's a short explanation again. So the barrier forces the speeders at the sync point to wait, and therefore we have this linear scaling. There are other ways to pin your threads to cores, like the shed affinity and so on. It's more work for the user. The user has to know the topology and so on. So that's why Liquid Pin provides you some helper functionality. So it's a semi-automatic pinning. Let's go into it. So Liquid Pin allows you to pin the threads and processes to specific cores without touching the code. So it's completely agnostic. We support pthreads, but also the various OpenMP runtimes and also other threading solutions like thread building blocks and Silk and whatever they are called. It's a combination of a wrapper tool for the command line and an overload library which overloads the pthread call. For that to work, the only requirement is that the binary is dynamically linked. And it supports like logical core numbering within a node. That's a feature which is not supported by any of the other tools. So let's look at the basic usage. So we specify the physical hardware thread IDs that are given by the operating system simply in a listed way or separated by comma, and then the application and the application parameters, and the Liquid Pin will take care that the application is using only these cores. We can also specify a different number of OpenMP threads. So if this application is using an OpenMP, we can specify the pin mask and then override the number of threads that should be used with manually setting OMP num threads. So the user is always in charge to specify what he wants. A simple usage for these logical core IDs, so the thread groups, is shown here in the bottom two lines. So for this, in the first line, we want from the socket 0, the first 8 physical cores. And in the second line, we want to do that for the second level 3 cache domain. So we specify so-called thread groups, which makes it easy to specify like an entity which is shared by a set of processors or a set of hardware threads. So like a socket or a shared cache. We define the thread group with a single character and an index. So here this S1 is for socket 1, here S0 for socket 0, and some others. And the important thing to note is that it uses physical processors first. So if we specify that, and this is our socket, it would take always only the physical processor and skip over the SMT thread. So we fill it up physical processors first, and then we do a wraparound and fill the SMT threads afterwards. Here are some of the thread domains, so basically all, except the new one. So a node, the node domain consists of all threads that contain are on a node. For a socket, we have the S prefix. For a memory domain, we have the M prefix. So in more recent architectures, sockets can have multiple memory domains. So this allows some separation for that. And with C, we have the outer level cache group. So in most cases, it's level 3. On the A64FX, it's the level 2. In the upcoming version, we have a new domain, D, for a CPU die. So also the A64FX is basically not 4 sockets, but 1 socket for 4 CPU dies. So in order to incorporate that, we add a new domain. There is some advanced feature. It's the pinning expressions, which can be powerful in situations where you have a lot of cores and a lot of SMT threads. So it can be long and clumsy. It's starting by an E, so it tells liquid pin to use the expression syntax. And then we set a thread domain like N or S, S0 or something like that, the number of threads, and then we can specify a chunk size in stride. This means we can select function-based wise in the node topology. So here in that example, we use 8 cores. We want to have 8 threads, but only 1 out of 2. So this would skip the SMT thread. This is an example for the Intel Xeon Phi, for example, where we have SMT4. So we take 2 threads out of the 4 threads per core, and we want in total 120 threads. And there are some helper functions like this mscatter, which scatters the threads over all of the memory domains. So that's it for the pinning syntax. So here, let's look at an example. We pin the standard stream benchmark to the first 4 physical cores of the socket 0. Liquid pin prints some output as soon as the threads get started. So it tells us that the main program is pinned to core 0. And then afterwards, each of the threads gets pinned to one of the remaining cores. If we set like an OpenPNUM thread to more than the cores we have here, it does some round robin pinning. So it starts again with 0 and pins the other threads. So this is the optional part. So I'm skipping over to the perf counter slides. Let's see. Wait. You should see the slides now. So The second part is about the performance analysis with hardware metrics or hardware performance counters, hardware performance events. For that, the Liquid tool suite has the Liquid perf counter tool. It helps you to find out performance properties and resource usage of parallel and also serial code, of course. Sometimes the usage of advanced tools like HPC Toolkit and vTunes is just overkill. You're interested in a single metric or something like that. For that, we can use Liquid perf counter, and it provides you 4 different measurement modes. So the first one is the normal wrap mode or end-to-end measurement. So it starts the counters, runs the application, and stops the counters and evaluates them. Then we have some kind of code instrumentation where the user specifies which region of code should be measured. That's the marker API. And then we have 2 more modes, which I don't want to talk today about. The stethoscope mode, which is like looking from the outside what the application is doing, and a timeline mode, which is like time-based sampling. The hardware performance events are pretty hard to manage. So the raw hardware events, for that, Liquid provides some pre-configured metric groups. They can be extended by the user, sorry. And you can get a list of those with Liquid perf counter -A. Here I copied some of the groups from A64FX from the Okami nodes. So like branch for the branch prediction and clock for clock frequencies. Flops, of course, there are different flops groups for the different positions, but also like L2 and mem for the resource usage in the cache and memory hierarchy. Here's some example. Liquid perf counter, then -G, and then we specify a group, so G for group. And with -C, capital C, we specify the threads we want to run on. It's the same syntax as Liquid pin. So all the Liquid tools use the same syntax and functionality. You can always use logical numbering, the expression syntax, or also these scatter things. It runs the output. So here we see the output, and then it prints which group has been measured, the raw events that are defined in a group, and then it prints the derived metrics. Those are the information most users are interested in. Hardware metrics or hardware events are commonly not what user look at. So here we see the runtime for each of the hardware threads we have specified. So here we see we have specified S1. So it takes the first socket, the second socket, and there we see we have the threads 12, 13, 14, and 15. So it automatically selects the proper cores for your pinning selection. And in the end, Liquid is using these 2 events to calculate the L1, L2 data bandwidth, and you get some nice output of the bandwidth and data volume, which you can use for setting up a module and so on. A model, sorry. So the marker API is for code instrumentation, to restrict your measurements to some specific code regions. You can turn the API is not doing anything with the configuration of the hardware counters. It's basically just reading them. The configuration is still done by the hardware, by the command line application Liquid perf counter. This makes it also very handy. You specify what to measure on the command line. The instrumentation calls are independent of the event set you specify. Here you see the calls for C. So we include a single header. Then we have a Liquid marker init in some serial part of the code. And then we specify different code regions with start, stop, and some common string for them. You can have multiple of these regions, like here we have multiple start stops. If they are called multiple times or traversed multiple times, the counts are accumulated. You can overlap these regions, you can have inclusive regions. And these are for the threaded parts of the application. And in the end, we call liquid marker close in the serial region again, which like writes out the results for the later analysis. These are macros, and you can activate them at compilation time with -d liquid perfmon. If you admit that these calls are empty and don't cause any overhead. Afterwards, you just use liquid perf counter like on the slide before, but add a -m switch for markers, which tells liquid perf counter to analyze the marker output. There is also a Fortran 90 API. Here is a tutorial for that. Just look it up. I have an example of an integrated marker API in Fortran program in a few slides. To compile it, just add the include part of liquid and the define. So here we want to have activated macros, and then we link it. We specify the libdir and the liquid library in the end. In most cases, these variables are handled by the module system. So in our case, at our center, our modules of liquid set these variables to make it more easy for the user to use the variable the paths. I added the path in the bottom for the Okami cluster. Then you run it, so liquid perf counter -C, then the CPU selection, -G, the group, and -M. You get one separate block of metrics and counters for each marked region. Of course, the marker API causes some overhead, so don't put it in too fine-grained into your application. So don't call it too frequently, these calls. So what to look at? So Georg already introduced our way of thinking. So we focus on resource utilization and instruction decomposition. So things like the operation throughput like flops, instruction throughput like CPI or IPC, breakdowns into floating point instructions, load stores, branches, and so on. SIMD instructions breakdown. So if possible, sorry, we can check whether we use scalar or like vectorized instructions, and also the data volume part and bandwidth, so the resource parts for the main memory for different cache levels and so on. Also things like clock frequency and the energy consumptions can be measured. Here are some of the groups which are commonly used for all these things that I listed above, like memdp, which is a combination of the memory bandwidth measurements, and flopsdp group. So it's combining floating point operations with memory bandwidth and gives you like already the input for simple models like the roofline model. memsp, same for single position. Branch for branching data for loads and stores and the load store ratios, and L2 for the level 1, level 2 cache traffic. Here's again like a grouping where you can look at. So that's like a stylistic node with multiple cores and different cache levels and so on. So you can look at the core, the useful work, instruction throughput, instruction breakdowns, at the load store operations between the core and the L1 cache, and also the data volumes and bandwidth between the cache level and memory. So here's a simple code example. It's a triangular matrix vector multiplication in double precision in that case here. So we have a loop. So we have a parallel region here, and then we run the loop, the main kernel multiple times, so k rounds. And here we do the matrix vector multiplication, but we don't do a quadratic or full matrix vector multiplication. We only do a triangular one. So here the j is starting at I. So to add the markers, we include the marker liquid marker header, then do some marker init before the parallel region, the marker close afterwards, and then we add liquid marker start and liquid marker stop in the k rounds, in the rounds loop. So each of the rounds is measured itself, and then the values are accumulated for the final evaluation. Same code in Fortran. So this is the Fortran marker API, quite similar. So also use liquid. Then we have these calls: liquid marker init, liquid marker start region, stop region, and marker close. If we run that, it's also on this A64FX node. We can see that the instructions are rising. So the number of instructions per thread are rising. So the first one is doing the least one, and the last thread is doing most of it. Why is this? Is that as Georg has introduced already, and I also introduced the implicit barrier at the end of the OpenMP loops. So since we have a triangular matrix vector multiplication, the threads are executing a different amount of work, and so we see that also they execute a different amount of instructions caused by the implicit barriers at the end. So what we should do always is to measure the actual work, which is in that case floating point operations. So if we do that, we see that the first thread is always doing most of the work, while the last thread is doing only a tiny fraction of it, simply caused by the triangular matrix matrix. What we can do, we can change the schedule. So if we open to the OpenMP do loop, the static 16 schedule, each thread is getting only 16 lines of the matrix, so it's more distributed, and we see that also the number of flops, or the number of executed floating point instructions, are evenly balanced. So no imbalance anymore, and if we look at the performance, it's also faster. Just as a short outlook for what you can use liquid perf counter, here's a picture of a roofline model that we use in our cluster monitoring toolkit. We print the number of jobs, so we print for each job we print a dot in this roofline model. That is all the data is gathered with liquid. And if you want to know how it works, we have this tutorial how to derive the empirical roofline model with liquid. So a summary about the hardware performance monitoring. You have to know what you're looking for. So you have to know some basic setting of the hardware and how it behaves. You can create a lot of data with it, but don't get any insights. So you have to know where to look at. In our opinion, the resource-based metrics are most useful. So like cache lines transferred, or data volume, bandwidth, and so on, load stores, the number of cycles, instructions executed, and so on. The CPI and also like cache misses may be misleading, as we have seen in the example. So just looking at the number of instructions doesn't help. We would also have seen that the CPI gets better if we have this load imbalance for the threads that do only a little work because the barrier instructions are fastly executed. A problem is, the problem is that processor work is not equal to user work, so like waiting times and so on. So we have to look at really the work that our application is doing. As we have seen, a useful application for performance monitoring is validating performance models. So we are using that to validate the ECM model and also the roofline model. Yeah, so it's a mighty tool you can implement, integrate in your workflow. Yeah, and with that, I'm giving over to my colleagues.
By the way, if you have any questions, feel free to speak up or type in the chat.
Okay, it doesn't seem like, right? Okay, so I'm Christie Alappat, and yeah, so I will briefly show you a demo on how we use liquid perf counter. So right now we are on a mission from University of Regensburg, and this is A64FX, and we are very thankful that they provided us this mission, because yesterday when we logged into Ukami and tried some stuff, everything was not working 100%. So yeah, we had to log in. We had to go to our colleagues in University of Regensburg, and we got our QPace system. Yes. So yes, first of all, with Liquid, you could try liquid topology, and with liquid topology, as Thomas mentioned, you can see the hardware topology of this machine. And as I said, this is FX700 system, so there are 4 sockets, each with 12 cores. So yes, so as for the first to run, I have here a matrix-free conjugate gradient solver. And let me see, yes, so there's an OpenMP version of the solver. And basically what it does is it has, in the main routine, it allocates some grids and initializes some grids. And basically at the end, the most costly part is calling this CG solver. And this is basically solving for heat equation. And therefore a 2D 5-point stencil is used. Okay? And yeah, the CG solver is pretty trivial here. Basically in the iteration loop, you multiply the matrix with the vector. So A with vector, but since we are doing matrix free and we are using stencil, we are just applying the stencil here. And then you have some dot products to do and some update. You are updating your solution vector x equal to x plus lambda b by calling this ax plus by operation, and again some dot products and ax plus by to update residual. Right. So this is basically a simple CG solver. And first, let's just run it. So I have compiled it, and it's here in MFCG GCC. So I compiled it with GCC compiler. I think I have enabled GCC, but so I have, I think, the GCC version 10.1. And yeah, so to run, let's first maybe run it with single core. So I can use liquid pin to only one core, so the core 0. And I basically do, and I just call my executable. Oh, yeah, so it breaks because I have to pass in the parameters, of course. So let's make the dimension of 20,000 times, 4,800 or something like that. And let's run it for 10 times, the iteration of the CG. Yeah, it should take some time because it's single core. but you see that Liquid already pins to hardware thread 0. So the main PID is pinned to hardware thread 0. Okay. So yes, hopefully it runs. Yeah, okay. So here we see the performance of the CG solver, which is given in megalattice updates per second, which is the output of the code, and also individual timings for different routines called in CG. So you have AX plus BY operation, you have dot products, so the timing for each of them, and timing for stencil, and the timing for the complete CG. So basically, if you add them up, it should, it should be almost similar to this one. But and if you now want to run it with 12 cores, so on first socket, you can do in this manner, because you see here in the topology, 0 to 11 is on socket on domain 0, so socket 0 or first NUMA domain. So right now I'm going to run it on one NUMA domain. And you see here in the output, the main thread is pinned to 0. The next thread is pinned to hardware thread 1, that is the core 1, then next to core 2, and so on. So Liquid does the pinning, and now I get a performance of 1580 compared to 274 for single core. And what you observe here is also for AX plus BY, it stopped scaling, something like, it's not like 1.25 divided by 12, but it scales by like a factor of 4, for example, here, right? So let's see, 1.25 by 0.34. Yeah, it's 3.6 or something, the factor. So it stopped scaling. However, dot product, what you see is it scales almost good with 12 cores. However, apply stencil, it again stopped scaling. So it's again like a factor of 6 between single core and multi-core with full chip. Not full chip, so with one socket. Yeah, and CG is basically the sum of them. Okay, so why is it that the dot product scales, but the others do not scale that well? Okay, so to find that, we can use Liquid, for example. And so we have to see whether it's a good thing or a bad thing. Right? And to do that, you can use perf counter to do the performance counter measurements. And let's measure with mem group. So this is basically Liquid has predefined groups where already the metrics are there. So as Thomas showed just now, and let's basically, yeah. Right now I'm pinning also when I'm running to the socket 1. So I'm running for 12 threads on socket 1. Okay. Yes. So okay. So basically here you see the mem groups. So the first are the events. So these are the raw events measured by Liquid. And yeah, so these are instruction retired, CPU cycles, and so on. But basically yeah, so these are raw events, and these are the counters that these events are assigned to. And also here you see the counts for different cores. So hardware thread 0, 1, 2, 3, and so on to 11. And here is a statistic of all the measurements between this 12 cores here. So you get the sum, min, max, and average here for each of these events. And then what you have is, this is basically most important, or what's more interesting for users. So Liquid basically does not just give out the raw event, it has some predefined groups, so that basically gets these events and with the help of this event, it generates nice metrics like memory bandwidth and so on. Okay, so here we see the metrics. So the runtime, okay, this is basically runtime, and the cycles per instruction is here for each of the cores. And then you have read bandwidth that you achieve for this entire code data volume that is transferred from memory, and from and to memory. From memory, this is read data volume, and then for the write and the total memory bandwidth and data volume. This is for each core, and then you have again the statistics for this metric table. Okay. Yes, but here we didn't use any marker, and therefore the results shown here are just end-to-end measurements. So you involve, so it's when starting main till the end of the main routine. Okay, so it also includes all the init function allocations and so on. So, and as you see here, the bandwidth is really not that good, because here you see it reaches maybe 44 gigabytes per second, but on one socket or one CMG of the A64FX, you should attain almost 200 gigabytes per second. But here you reach only 44 gigabytes per second, because you're including all the other effects like initialization and stuff, and you run just for 10 iterations. But you can go deep, and you can monitor each of the functions with the help of markers. So this is where the markers come into play. So let's go into a code which has already been, where already markers are added. So basically what you need here is, add the liquid.h. So include liquid.h. And then basically, let's see where liquid is being.
I'm sorry to interrupt you, Christie. I'm just wondering if there are any participants left from overseas.
That's a good question. I have to accept it, huh? Is it already? Okay, I think it's fine. Okay, yeah. So basically what you need to do is to add markers to, so where you have to measure, for example. Here, for example, you have AX plus BY operation. Basically, it does this operation. So you have A times X vector plus B a scalar times Y vector. So A and B are scalar, and it adds the result to this. Okay. And yes, so you add in the markers, liquid marker start. So you tell the performance counters to start, and then you tell the performance counters to stop. Okay, and it has to be taken care that this marker start and stop is already done within the parallel region. Okay, so you add for the functions that you want to calibrate or measure, monitor with performance counters, you add the markers. Right, so here dot product, apply stencil, and so on. So that's the first thing that you can do. And then in the main routine, or when your program starts, the first thing to do is call liquid marker init. Okay, so in the main, the first thing to do is call liquid marker init. And then you can optionally call also liquid marker register. But this is a good practice to do liquid marker register, because this reduces the overhead that's incurred when calling for setting up the performance counters. So if you first call liquid marker registers, the setting up the counters and stuff is done here. Else it would always be done in the first call to liquid marker start, and this might involve more overhead. Okay. And at the end, what you do is just call liquid marker close. Okay, so that's it. So at the end of your program, you just call liquid marker close. Then basically you can compile the code. Yes, so I use GCC here. I added some SVE flags for GCC, and OFAST. And here I have to define liquid perf mod, so that so inside the liquid marker starts and stop is activated. So it's important that you activate the liquid perf mod. Okay, so you define it. And then I have this include. So I include the liquid directories. So the header file where it's located. And I also tell where my liquid library is. And basically then, yeah, I tell, okay, to find a liquid library, and I compile it. Okay, once compiled, what you can do is, so this was how I ran previously. Now what I can do is I can run with markers. So if I run like this, it would be the same output without any, it would be the end-to-end output. That is from the start of main to the end of main. You won't get the readings for each of the function. So to get the readings of each of the functions that you have marked, you have to add -n. Yes, so let's do it for single core, so it's much more easier to understand first, probably. Yeah, takes some time. Single core. Yeah, by the way, the dimension of the stencil or the total grid size is 20,000 times 4,800 in this case, and I do 10 iterations. Yes, and now here you see for region AX plus BY, so that's what we call the region, so liquid marker start, and in the parenthesis, I specify AX plus BY, that's why the region is also called AX plus BY, so that's where the name comes. And it's measuring mem group because I specified to, yeah, measure mem group. Yeah, these are again the row events. Yes, these are, so these are again the row events, and then you get the metrics which are derived from this row events. And here you see for AX plus BY, on one core of A64FX, I get 55 gigabytes per second. For dot product, I see I can get some 16 gigabytes per second. For apply stencil, I get something like 24 gigabytes per second. And for conjugate gradient, the entire solver, so this includes all of this, okay? So AX plus BY dot and stencils, it gets something like 32 gigabytes per second. Okay, so this is just to see. And now if what happens if you run with full socket, full one socket. So let's see what happens. So remember for this system, the bandwidth is almost 200 gigabytes per second. Yes. So see, let's look from the beginning. AX plus BY, you see memory traffic of 200 and almost 210 gigabytes per second. So it's good. So it saturates the main memory bandwidth without any problem. So you see, okay, this kernel is good, AX plus BY. For dot product, if you see, oh, this is problematic. There can be more optimizations that could be done because here you see the performance or the bandwidth that the dot product draws from main memory is somewhat 171 gigabytes per second. But normally, if you see dot product, it has it does 16 bytes and per 2 flops. So basically, it should be highly bandwidth bound, but it doesn't saturate the main memory bandwidth. So there is some problem with dot product, which we will analyze just now. Let's see, apply stencil. So this is the stencil. Main memory bandwidth is 200, almost 200, more than 200. So it's fine, it saturates the main memory bandwidth. And yeah, for CG, it involves everything. So yeah, so it involves everything. So basically, it's more helpful to analyze kernel by kernel rather than the entire algorithm. So here, there would be some performance loss from dot product and stuff because it doesn't saturate, so on. Yes. So yeah, but why is dot product having such a low bandwidth? For doing this analysis, we have to go deeper. Basically, what one step we do normally is check the assembly code in these cases. Okay. Let's do that. So this is the output. So I'm generating the assembly code for this. So let me search for dot product. Okay, this is the dot product code. So yeah, and yes, so this should be the main routine which does the dot product. So this one, L57, because it does two loads, because for dot product, you load two arrays and you multiply them and sum them up, right? So you load two arrays. So this is SVE instruction set using SVE. And this is for loop implementation using add, and then you basically do an multiply and add on these two loaded elements. Seeing this, it's good, seems like good, like it's vectorized and stuff, but still this code doesn't attain the main memory bandwidth saturation. So yeah, for analyzing this, I would transfer to my colleague, Jan, who is expert in analyzing the INCO problems. So Jan, maybe you can.
Thank you, Christie. Let me try to share my screen. Yeah, I think this means it will automatically end your sharing. Sure. Right. Here we are. All right, I hope you can see my screen.
Yes.
Sure. As Christie already explained, I isolated the kernel he just showed. You see it's a different label here, just because I compiled it already, not live now, but had it before. But otherwise, it's exactly the same code. We have those two loads Christie talked about, our FMLA, and the rest is basically loop overhead up to here. And as Georg already mentioned in the beginning, there's this tool called OSACA, which we use for in-core analysis of such kernels. And OSACA needs a in-core model, a hardware model, for analyzing a code for a specific architecture, which we can see in some kind of ASCII art here on the right part. So for the A64FX, we have different ports numbered here from 0 to 7, which can be used for different functional units. So as you can see, FLA and FLB do the floating point arithmetic here. FLA is also used for storing data, while EHEA and EHEB here are used for loading data. And then we have some integer arithmetic for EXA and EXB. So OSACA can take this and put this in context with our code. So for this, I already have it installed here, obviously. We have different options, but what we need to do first is somehow mark our kernel, because normally it's not as isolated as I have it here. So I would simply add something like comment markers, OSACA begin, and our loop ends here. So we would put a OSACA end here, because those last two lines of code are actually done after the after all iterations. So I will save that and then simply run it for our A64FX instruction microarchitecture. Sorry, it's called .product, and hopefully we get an output. Looks good. So what you see here is basically the same as our port model on the right. So the 0 stands for our floating point port FLA, and so on up to 7 for our branch port here. And the output I'm highlighting here is our throughput prediction for this kernel. So if we don't have any dependencies and everything can run independently, iterations can overlap, then we would see a port pressure of this as a throughput. So we would expect the code to need only one cycle per iteration, as Christie said, totally bandwidth bound. But what OSACA gives us as well is some kind of dependency analysis. So that's why we have those two outer right columns, and LCD stands for loop carry dependencies. So it detects not all of them, but register dependencies dependencies between two loops. And here we can see our FMLA fused multiplier, and that is reading from our C0 register, but it's also writing on it. So for our next iteration, we actually have to wait until this instruction is done, and we pay the price of the full latency for this instruction here. So we can see, or we would expect, one iteration to take 9 cycles instead of the independent 1 cycle per iteration. And if we would measure that now, I think we don't have the time for this now, but we would see that our performance actually gets to this roofline of 9 cycles per iteration.